Well, hello everyone. Welcome to Global Compliance Panel's live webinar on statistics for quality control and processes validation, basic factorial designs. My name is Johnson and I'm going to be your host today. On behalf of the Global Compliance Panel team, I would like to thank you for being a part of today's event. Today's webinar will be presented by Dr. Stephen S. Kuwahara. Dr. Kuwahara is the founder and principal of GXP Biotechnology LLC, a consulting firm that works in areas covered by the GLP and GMP of drugs, biologics, and nutraceuticals. Dr. Kuwahara has over 30 years of experience in supervising quality control laboratories, including an animal testing facility, and in performing GLP and GMP audits of internal and external testing laboratories. Dr. Kuwahara participated in the development of drugs and biologicals through all phases of clinical research and final product production. We are honored to have such a distinguished person such as Dr. Kuwahara with us to present today's webinar. Before we begin, I would like to inform all our participants of the program outlined for the training session. This webinar is for 90 minutes duration. First, Dr. Kuwahara will take you through today's webinar, highlighting the areas that would be covered, and he would then share with you his presentation. We would like to inform all our participants once part of the teleconference have been placed on mute and will remain so until the Q&A begins towards the end of the webinar. We also request all to hold back your questions until the Q&A window begins. 10 minutes of time is allotted for the Q&A during which all your questions will be answered. If for any reason you do get logged out of today's training session or teleconference, please follow the same procedure to join in again. Now that we are all ready to start, I would request Dr. Kuwahara to take it from here. Doctor?
Okay, I guess you need to give me back my, there we go, I've got my pointer. Okay, today we are going to be talking about basic factorial designs. Now, this talk is actually part of a series of talks, and the preceding webinar would have covered things like basic ANOVA, analysis of variance studies. And we are going to take off from there and go into so-called factorial designs. Now, what I'm going to show you here today are the very early forms of what is known as the design of experiments, or the DOE procedures. And what we're going to do here is to make the transition from ANOVA, simple one-way ANOVA studies, into the more complex level of factorial designs. And I'm not really going to get into things like response surfaces and the like, or things that require fairly complex statistical packages in order to do properly. What I am going to show you are some basic factorial designs, and I will try to point out to you where I can how these designs can be extended so that you can do more than one study at the same time. And this, of course, increases the efficiency of your work. Now, the thing about this whole process is that one of the things about statistics is that if you look at the total number of experiments that need to be done for any given situation, the complexity and level of experiments goes up geometrically. And as a result, people shy away from these experiments because they feel it'll cost too much, it's too complex, etc., etc. Nothing can be further from the truth. Actually, if you do a proper factorial design, what you will find is that it minimizes the total number of experiments you need to do in order to obtain solid results. One of the big problems that we find, especially in the pharmaceutical area, is that people do single factor studies, where you keep everything constant and then you only vary one factor. The problem with this is that reality is not a single factor. Reality has multiple factors, some of which interact with each other, and all this sort of stuff. And so when we get into our actual work, the single factor experiment does not really represent what we are seeing in our work. So what I am going to do here today is to try and take you through a very basic and early forms of factorial designs, and hopefully from that you will be able to see how you can extend it. And the other thing I'm going to do is I'm going to show you how this is calculated manually. I do agree that you do need software packages if you're going to do a lot of this work, but it's critical that you understand what is going on inside of your software package. And if you don't understand these things, it's easy to be misled by your software package, and then, well, all sorts of unfortunate things happen, including things like coming to the wrong conclusions and basically making life hard for yourself. So let's get started here with some really basic forms of factorial designs. Now, what we're going to show here are two-level designs, and I will admit that, yes, if you really want to read things in the back of the statistics textbooks, you will be able to see something more than just two-level designs. However, this can create some problems for you in your work. Now, the simplest factor design is a two-factor, two-level design. In other words, this is basically a 2x2 experiment, and yeah, okay, anybody can do that, and anybody can do it on paper. But these are simple and sort of, well, I just want to give you an introduction to what is going on here. Now, the factors that we're talking about here, these two factors, these are things whose effects you want to measure. Now, these are things like time, temperature, etc. Now, notice this. You don't have to have a quantitative factor. Factor can be something simple. It can be color, black and white, pink, blue, something like that, male or female, all this sort of, in other words, it can be a qualitative type of thing, but qualitative in the sense that you can clearly differentiate between things. Now, one of the problems, especially with things like color, is that, you get into this thing of, well, I just had a recent one where a person sent me a spec that said white to off-white. And my question was, what do you mean by off-white? Do you mean pinkish? Do you mean grayish? Do you mean brownish? Or is it just sort of a diffuse gray? And the thing is that if you're going to use things like color, you must have a very clear definition of what your plus state is and what your minus state is. The levels, they're usually shown as plus or minus. And this is for convenience in designing the experiments and thinking about them. But it's not a true plus and minus. It can be high, low, present, not present. In the case where we test workers, for instance, it can be two different technicians. It can be two different workers, etc., etc., and they can be, of course, nobody wants to be the minus worker, but, well, that has to be done. It's anything that you can differentiate. And literally, you can have things like happy, unhappy, and again, you come into the question of exactly how happy are you and how unhappy are you. But The thing here, and this is very important, you have to sort of judge how far apart you want to make your plus and minus, especially when you're dealing with quantitative things. If you make the plus and minus too far apart, then yeah, you probably will pick up a problem. But what you want to do is to cover the area of interest, in the area that you're really concerned about, whatever is practical for you. At the same time, if you set the plus and minus too close to each other, then there may be an effect out there, but you're not going to see it because you just don't cover that area where you might have a problem. So you need to set your plus and minuses over the area of your concern. And for most of us in the pharmaceutical business, the plus and minus will be the range of your specification. You usually set your specs having a plus minus to them. And so the plus would be the high and the minus would be the low end of your specification. And this is a good starting point. Now, I will tell you that when you're doing studies to define your design space, you might want to make the plus and minus actually wider than your normal specifications. This is so that if you should fall out of specification, you have a little area to operate in where you can then argue that there is or is not an effect. And so, just sticking strictly to your specifications is not necessarily a good thing. Now, we're going to get through, in going from a two-factor, two-level design, we're going to go and look at a very basic three-factor two-level design. Now remember, two levels say, plus minus, that's two levels. Three factors will be A, B, and C. Now here's the thing, OFAT studies, one factor at a time studies, in order to get the same amount of information, you need many more OFAT studies than you will get from looking at a factorial design. These create the minimum number of experiments that you need, and the problem here is, remember this, if your factorial design says that you need to run 8 experiments, and for various reasons, including cheapness, you decide that you're only going to run 6, or you're too tired to run 8 and you're only going to run 5. Remember that when you do that, you're going to leave holes. In other words, holes in your logic, holes in your experimental results. So the problem with factorial designs is that when a factorial design says that you need to run 8 experiments, that's it. You don't go below the 8. Now, when running an experiment, you may see more than one effect. In fact, you can measure more than one effect. To a certain degree, it's limited only by your abilities as analysts. But however, you do look at them one effect at a time, and I'll show you this in a design that's coming up. Now, with basic two-level designs, this being the old plus-minus business, the number of experiments is a power of 2. So a three-factor two-level design, it requires 2 to the n experiments, or in this case, 2 cubed. N is the number of factors that you're looking at, and we're looking at 3 factors, 2 levels, so it's 2 cubed, which is 8. And so we'll talk about a design here that uses 8 experiments. Now, here's a 3-factor, 2-level design, and this is what is called a general design here. We have the 3 factors, A, B, and C, that are basically just codes. You'll see later on we'll assign something meaning to A, B, and C. Here's your setups. There's 8 experiments, remember that. And one thing you're going to notice here, there will always be a row of all minuses. That's one of the basics here. And then, however, in your run numbers, notice this, your run numbers are scrambled. And that is done deliberately because we know that if you were to take these experiments and then just run them in the sequence of the setup, in other words, 1, 2, 3, 4, and run them in that order, that if there's some sort of systemic error in your process, then what will happen is that this error will build into your test results and affect your general conclusions. So what you need to do here is to run them in randomized order. And this can be done using any sort of randomizing procedure you want. The easiest one being, of course, to, in this case, just write 1 to 8 on pieces of paper, throw them into a box, and pull them out one by one blindly. Now, you see, here's the thing. Suppose we had a situation where we can run one experiment in the morning and one experiment in the afternoon. If we ran these things in order, then all the even number experiments would be run in the afternoon, and all the odd number experiments would be run in the morning. Now, when you figure, okay, your workers come to work, and some of them are very fresh in the morning and get tired during the day. So the work that they do in the morning is much better than the work that they do in the afternoon. Now, of course, we all claim that this will never happen, but it does. And so what will happen is that the even-numbered experiments will be performed by tired people, whereas the odd-numbered experiments would be done by people fresh into work. And so your results can be affected by this sort of thing. Another one is, in some places there are differences in the equipment. Equipment is running smoother in the afternoon, or for whatever reason. And so this is the reason you really do have to scramble your experiments and not run them in sequence. So you can see here we've drawn up a set of 8 numbers out of a hat, and we have these run sequence. So actually, setup number 2 is the first experiment done, and setup number 1 is the 8th experiment that is done. Now, when we run these experiments, we have a result, right? Whatever you're looking at. And this would be the result, and this is assigned Y1 for convenience sake. And then, we can also take the same experiment. You have this product that comes out, and you can measure Y1, but you might also want to look at another property of the product, and that can be result Y2. And so these measurements, actually, notice this, you could go out to Y3, Y4, etc., as many as you have the capability of measuring. So, this experiment right here, you run one experiment, but you can look at several effects out of that experiment. So again, you have efficiency. You have the minimum number of experiments that produce, give you effects and allow you to look at a lot of different effects. Now, here's a case here. We said we would look at this 3-factor 2-level. Okay, here's the factors. Here's A, B, and C that we talked about. And what have we done? Well, what's the name of the factor? Okay, A is the supplier. The unit of the supplier is who? Who's the supplier? And the low supplier is supplier B, the high supplier is supplier A. And you wouldn't even necessarily just use A and B. You could just put in the names of the suppliers. Factor B is a mixing time for this. Well, it turns out we're using an API here and reacting the API with another substance to make a product. And so we have a mixing time here. You dump the API in and you mix it for a while. How long do you mix it? And in this case, the unit will be in minutes. We have a low side of 4 minutes, high side of 6 minutes. Again, there's no restriction. This could be your spec for the step. You could say, well, okay, you're supposed to run for 5 minutes, but we will look at the high-low here, which would be 4 and 6. So your spec for this step would be mix for 5 plus or minus 1 minute. Similarly, the factor C is now the power supplied to the mixer. And what you can look, there's many different types of mixers, of course, but this is sort of a measurement of how energetic is your mixing. And the unit here is percentage. We run at 100% power, or on the low side, we run at 75% power. And so these are our 3 factors. And so now let's take a look at the experiment here. We have, again, this experiment. We've run it. This is the same setup you saw on the other side. We have 2 sets of results here, and I will tell you right now. Result number 1 here, Y1 is the product yield. Y2 is it's the measurement of an amount of impurity present. And so we can look at this, and this now corresponds to these setups. But the question is, okay, what's the effect here? How A, B, and C? What happens here? So we have this thing here. This is the effect. And effect Y1, we would take the results here and use them to measure effect Y1. Effect Y2, we would take this set and calculate effects here. Now, let's take a look at this. Now, the effects that we're looking at, they're also known as contrasts. Statisticians who like to look at these things in a geometric form, you can consider this as looking at the front face of a cube versus the rear face of the cube, and that's the contrast between front and back. The effect is calculated by doing this. You sum up all of the pluses, okay, for a given thing, factor, and then divide that by the number of the pluses. So we have the pluses, the average pluses, minus here the average minuses or the negatives, and then divided by the number of negatives. So actually it's pretty simple. You're just contrasting the pluses with the minuses. Now, take a look at this. Okay. Remember the A effect. If we go back to the experimental design, we will see that the A effect coming down this way. The positives are here. They're at 2, 4, 6, and 8. The negatives are the odd numbers, 1, 3, 5. I mean, the negatives are rather 1, 3, 5, and 7. Now, one of the things that you need to, okay, excuse me, I shouldn't have done that. I'm getting ahead of myself. Okay, but you can see where the plus results are and the minus results are. We don't question B and C at this point. We just look at A. And so when we get to this slide here, we have here the A effect is the result, experimental result from experiments 2, 4, 6, and 8 divided by 4. Remember, divided, it's the average pluses, minus experiments 1, 3, 5, 7 divided by 4. All of these added together divided by 4. So it's this number, these numbers here. Those numbers correspond to these numbers here. 75, 80, 77, 32 added together minus 74, 71, 81, 42. And this gives you the A effect. Now, interestingly enough, for this particular experiment, this is the effect of the supplier. So right away, we look at this result and say, yeah, it's not very big. It's probably not a very great concern. So right here, we kind of know, okay, it's actually -1 is the result here. And so there's not too much of an effect of the supplier. However, when we look at the B effect here, positive B's, 3, 4, 7, 8. Okay, we go back here. Where is B positive? B is positive in 3 and 4, and then again in 7 and 8. And you have a corresponding result. So we take that and we subtract from it the results of 1, 2, 5, and 6 divided by 4. We get that. Now we have a B effect of -20.5. Now this is getting a little interesting. In fact, what we're seeing is that B does have an effect on the results, and it's kind of large. Basically, you've reduced yield by 20.5 units, depending upon how you did your results. And you can see, you can do the same thing for the Y2 measurement. And in this case, Y2 is an impurity that you're trying to control. And you can see that, again, it doesn't make too much difference which supplier you have. The amount of impurity is the same. However, B, and notice this is minus. So it says that increasing B, okay, can lead to an effect here. And it's not very large compared to the A. The A effect is minimal. And but the B effect here for the positive B's or minus B's is 20.5. So that's large. We want to take a look at that. I'm leaving C out here because, well, basically I don't have space. But now we can insert all the results here, and we can look at this thing and say, okay, A, which was the supplier, the effect of that plus minus is -1. So we really don't care. In terms of yield, the effect of the supplier is minimal. However, in terms of the product yield, B, the mixing time, does have an effect. It's a negative effect. And also the power supplied to the mixer has a negative effect. And so notice here, your impurity, however, which was the Y2, it doesn't change all that much. It does go up a bit with the change in mixing and mixer power. But down here, we're looking in terms of yield, we definitely have a problem with B and C, with mixing time and yield. Now, the other thing here is this. I show an average. These averages become important later. But the results here, this is the average result from Y1. And there's a corresponding thing for Y2. We're going to kind of start to ignore Y2 here because this being the impurity, yeah, there seems to be an effect, but it's not very great. So we're just going to worry about the effect on the yield. Now, we come out here, and there's two things here about a three-factor, two-level design. Okay, we had looked here, A, B, and C. Now, what the heck are these guys here? These are interaction effects. Those of you who have looked at things like design space studies and things, interaction effects are sometimes also referred to as synergistic effects. In other words, B and C in this case, the interaction between B and C is greater than what you would expect from just adding B and C together. And so you get a BC effect, an interaction effect. Similarly, there's an AB effect. And there's a couple of things here you need to know. Okay, how do you calculate or how do you determine what the A, B, and C, what the factors are, whether they're pluses or minuses? And the way this is done is by doing algebraic multiplication, which is, not a tremendous intellectual feat. But anyway, the AB effect is the product of A times B. So a minus times a minus gives you a plus. The BC effect is B times C. So a minus times a minus again gives you a plus. ABC, which is a three-way effect. This happens when A, B, and C come together all at the same time. This effect is a minus times a minus giving you a plus times a minus, which gives you a minus. Okay? Similarly, when we look down here at the AB effect, from here, A times a minus, AB effects are from a minus, plus rather, times a minus. This gives you a minus. The AC effect is a plus times a minus, again giving you a minus. The BC effect is a minus times a minus, which gives you a plus. The ABC effect is now here's the thing, plus times a minus, which gives you a minus, times a minus, which gives you a plus. Okay? And so we get these columns here for the interaction effects. We can generate that. Now notice one thing here. What we have looked at, there are 7 effects that we have measured here. Okay, this is the main effects, A, B, and C, and then these interaction effects, which is AB, AC, BC, and ABC. And this is one of the rules with factorial designs. You run 8 experiments and you measure 7 effects. And this is one of the rules. It's all the number of experiments you run, the number of effects that you can see is n minus 1, always 1 less than the number of experiments you ran here. So we had these results previously, we had these results here, and we had these effects that we saw as the main effects. We go in and look at your interaction effects, and we do this again the same way. the AB effect, we add the positives, divide them by 4. We add the negatives, divide them by 4. And we get this. And the AB effect is 0.5. So we kind of look at this and we say, well, okay, the interaction between supplier and mixing time is minimal. However, when we look at the interaction between the mixing time and the power, we find that we get a significant effect here. This is the BC effect. Now notice this number, the fact that you have a large number here, tells you that an interaction is occurring. It doesn't have to be bigger than the B effect or the C effect alone. But the fact that these two create a larger number tells you there's a problem here. However, there's an ABC effect. And remember, we had a column with ABC. Notice this, the ABC effect is rather small. So we're saying, well, if you look at all three of the factors, and we look at all three of them influencing each other, the effect is not very big. Even though we know that buried in here, there's a BC effect. But when we break it out and we look at the BC effect, we see that this is much larger than either the AB or the ABC. I can tell you the AC effect is similarly relatively small. So now we're saying, okay, we don't have to worry about a three-way effect, and our ABs, AC, not so much. But yeah, there is a problem at where B and C are interacting with each other. So we come back to this table here. We now fill in all of the columns here. Now, we still have this average response, and I've got a note here saying it becomes important later in the discussion. But, you can calculate this. Now, notice that everything we have done to this point can be done with pencil and paper or an electronic calculator, which I understand some of you don't know how to operate since you're so computer dependent. But anyway, the calculation can be done pretty much simply with pencil and paper. But we look at these effects and we say, yeah, the mixing time has an effect. The power of the mixer does have an effect. And the power of the mixer and the mixing time, yeah, they do have a joint effect. But, three ways, not so much. And the supplier versus the power fed to the mixer, yeah, that's not so much either. And we know the power versus the mixing time, the supplier versus the mixing time doesn't have much of an effect. So we know what to concentrate on here. And this is, at this point, for those of you who do development work or, are working with actual processes in the manufacturing area, this is telling you that there is a problem here with your power and your mixing time. And this is where what you need to control if you want to maximize your yields. Because mixing time and power is having a bad effect upon your yields. It's a negative effect on your yields. Now, okay, some conclusions here. There's 8 experimental runs, 7 effects. And I think you can see that, we could expand this. And quite frankly, if you go into the statistics textbooks, there are other designs that are set out there for you to just look at. We don't have to just do 3 factors. We could do 4, 5, 6. In fact, there are several studies. The classical one being, well, there's some very large screening studies that you can do that don't require a lot of experiments, but where you can draw a lot of conclusions from them. I am showing you here probably about the simplest of the factorial designs. And then there's also what are known as fractional factorials, where you do eliminate some of the interactions and things like that. And you do reduce the total number of experiments that you have to run. It's 2 to the n power minus a certain amount. And these designs are in the statistics textbooks, and you can look at them. But when you look at them, you should always realize that you pay a price when you don't look at the full factorial designs. And the price comes in the form of things that are known as compounding and similar things that if you understand what's going on, it's not so bad. If you don't understand what's going on, you will be fooled. So, be very careful when you start to do these things. But here's the thing. See, raising the time or the power alone had strong negative effects on the yield, which was even worse if both were raised together. So at this point, you have to start doing experiments on the time and the power that you're feeding into the system. And the other thing you should note here, most common in their interactions are two-factor. Three-factor interactions are not so likely. This is the same thing as those of you who've done enzyme kinetics. It's the probability of three things interacting all at once. The probability, for instance, of three molecules coming together all at once. Usually it's a lot easier if you just consider everything as two molecules coming together and then maybe making a product and then that product reacting with another molecule. Same thing happens here. The probability of, suppose you had 4 or 5 factors, the chances of them all coming together and creating a interaction is not very good. The probabilities are low. This is why in the more advanced designs, you will notice that most statisticians only worry about 2 and 3 factor interactions because the probability of a 4, 5, or even higher level interaction is extremely low. And so they will kind of avoid working on that. By the way, I'll point out to you right now, I am not a statistician. Basically, I'm a QC chemist, a QC analyst that learned to do statistics sort of as a matter of self-defense and also as a matter of trying to figure out what is going on with a lot of my work. Now, we go through these factorial designs. Now, here's the thing. What you just saw is called an orthogonal array. It's the standard array, the ABC and 8 experiment. Remember this, the treatments A, B, and C must be independent of each other. Okay, you cannot have a situation, for instance, where the mixing time and the power fed into the mixer are dependent upon each other. Then, that sort of, follows up the experiment, basically. You have to be able to assume that you can set mixing time and power into the mixer as 2 separate things, not dependent upon each other. Naturally, the supplier was independent of all of that. Now, the array must be balanced. For instance, when C is at the minus level, and you look at C, all the minus C's, when you look back at the A and B's, there should be an equal number of plus A's and minus A's and plus B's and minus B's. And the same thing is true with C. Like if you look at the plus A's, all of the plus A's should have an equal number of plus C's and minus C's. This whole thing comes into the array. Now, as I say, these generate 2 to the n power runs. You estimate 2 to the n power minus 1 effects. And these are called orthogonal arrays or orthogonal factorials. There are also what are called orthogonal fractional factorials. The whole thing, the reason for the fractional factorials is that because you're following an exponential, this n here, full factorial studies become unwieldy. I mean, you know, it's 2 to the 2 cubed, 3 factors. When you go to 4 factors, you go to 16 experiments. When you get to 5 factors, you're looking at 32 experiments, et cetera, et cetera, et cetera. And pretty soon, the number of studies you need to run becomes unwieldy. And this is why people have come up with fractional factorials. Now, the questions often arise. How the heck do you know what is significant and what is not significant when you look at these effects? In this particular case, you know, the B and C and BC effects were pretty clear. They were well separated from all the others. But suppose you are in a situation, and in this case, in the impurity study, there's some results, okay, where the one interaction is twice as large as the other interaction, and yeah, well, we don't know if that's a significant thing or if it's just random error. You see, this is the whole point to these designs, is that you're looking for the difference between the results of random error and actual effects that you can measure and work with. Now, here's a method that is used. It's quite common, actually, among statisticians. You use a thing known as the half-normal plot. Now, I'm going to tell you, I'll warn you ahead of time. In doing a half-normal plot, you need to have access to a statistical software package, or somebody who really knows how to set up graph paper. There was a time when you could purchase this type of graph paper in student bookstores at the universities and things like this. And I have discovered by personal research at places like MIT and the University of Pennsylvania, Cornell University, Wisconsin, that they don't sell it anymore. And the easiest way to get it now is to have a software package that will actually print the graph paper for you. However, if you want to do it by hand, here's the thing. First, you convert the effects into absolute values. In other words, you don't have pluses or minuses. They're all just plus numbers. You can think of them that way. And then you divide 100% cumulative probability into 7 equal segments. Okay? Now, why are we doing this? It's because we have 7 effects that we're looking at. So we're going to plot 7 points, and we need to divide the 100%. Now, remember this. This is cumulative probability. And then you create a graph using this with the effects on the x-axis and cumulative probability on the y-axis. And we're looking at this here. Here's your effect. You know, these were the effects, and these are put down in order of magnitude. Okay, so the AB effect was the smallest at 0.5, the A effect at 1, etc., etc. And we have BC at 21.5. And then the cumulative probability is shown here. Now, we're going to plot the midpoints of the cumulative probability. So actually, if you divide 100 by 7, the first point should be 14.2857, but actually the midpoint of that range is 7.14. So here's 7.14. And all of these guys are set up at the midpoint of the cumulative probability range. You know, you jump. First point is here, you add 14.2587 to the next one, and then take the midpoint of that new range, you get this, etc., etc. Okay, and then you will get a piece of paper that's set up like this. Notice this cumulative probability starts off here small, and there's a spacing here. This is not basic log paper, by the way. It's probability paper. So here's what we get. And you can, this curve here is the half normal probability, right? You see this thing, it's actually a bell-shaped curve. But we're putting this thing, 0 is at the middle of the bell-shaped curve. And so we start to get cumulative probability 7.14, the 21, the 35, etc., etc., going up to the last one. So we then plot, here's the effect along here, and we plot them, the 0.05, the 0.1, etc., etc. Now, there's an interesting thing that happens. If these results are normally distributed error, okay, this, you have to remember this. It has to be normally distributed error. They will fall along this line here. They will all fall in a straight line. If they all fell in on this straight line, you could say that this is nothing more than random error. We're seeing the effects of random error, and we could, sort of ignore them. Now, one of the rules that statisticians will tell you is that, you don't expect the points to exactly fall on the line. And there's various rules that people have developed. One of the simpler ones is that if you can lay a pencil down along these lines and they still form a straight line along the pencil still looks straight, then, it's probably a random error. Now, what happens here is that when we go to plot the C effect, the B effect, and the BC effect, we find that they are off this line. And because they're off this line, they have to be significant. In other words, we're not seeing random error. We're seeing an actual experimental effect here. So from this, we know that these guys down here are not significant. They're just part of random error. It's the C, B, and BC. These are real effects. They're not due to error. Now, basically, we're looking at a half normal curve. And one of the reasons we got away with this, remember, was because we used the absolute values of the effects. And that's why we only needed to use half of the curve. Now, these are randomly distributed here, AC, ABC, AAB, and not significant. These were significant. Now, you want to protect yourself by using an ANOVA. And one of the ways you do this, you want to have a higher degree of certainty. You see, one of the troubles with a lot of these DOE designs, fractional factorials, is that, you could be having drawing the wrong conclusion, again, because of random error. So one of the things you want to do is to do an ANOVA on your results and an analysis of variance. And to do this, you need to know what is called the sum of squares. And fortunately, we already know the effects. And the effect is actually the same as sum of squares divided n divided by 4 times the effect squared, and I see the parentheses didn't come out correctly here, but this should be a closing parenthesis with a 2 superscript so that you have a 2 to the power, and this where n equals the number of runs, where in this case it's 8. Okay, so it's the effect times 8 divided by 4, which is 2. And remember, the equation only works for balanced two-level factorials, or orthogonal, whatever you want to call them, but two-level factorials. Since all of these were since these guys were random error, we use them to estimate the noise in the system. You know, this is called the residual sum of squares. In other words, the background noise caused by random experimental error in your system. And in this case, it's called the residual sum of squares, and it's the sum of squares, the sum of squares of all these guys. Okay? So this is the residual, which is 99. We do an ANOVA table, and remember, in an ANOVA table, there's the mean squared error, which is the sum of squares divided by the degrees of freedom. And we set this out. Okay, now here's the sum of squares. And one of the things I want you to notice is this is the model sum of squares, which was, you know, the factorials that were studied. This is broken down from this. So these, in this case, we are able to break down the ANOVA study to the point where we can see the effects of the individual factors. But in a lot of ANOVA studies, this would not be possible. We would just have the model here. And then we have the residual, then we have the so-called total sum of squares, which is nothing more than the model sum of squares plus the residual. Degrees of freedom are 7 because we had 8 experiments. Remember, it's n minus 1. The model has 3 sum of squares, okay, that has 3 degrees of freedom. The individuals here were 3, which add up to this 3. And then the residual, there were 4 residuals. Remember, these are the effects, right? There's always one less than the number of experiments, so it totals to 7. So now we have the mean squares, which we calculated here. This is divided by 3. All these other guys are divided by 1. This one's divided by 4. Now the F value is the residual mean squared error divided into the mean squares for these other guys. And this is the F value. For those of you who worked with F values before, F should be, if it's greater than 1, it's usually significant, and especially if it's much greater than 1, all of these are significant. The probability of getting these numbers by random error is much less than 1%. So in this case, we have confirmed that the BC and BC effects are for real. They really are significantly different. The last step you can do is you can do a linear model. And this is the thing. With one factor, this would be your linear model. And the betas here, especially beta 0. Beta 0 is actually the intercept of the equation. Notice, you know, this is the equation of a straight line. Beta 1 often is called a slope, but it's not really. If you're doing linear regression, this would be the slope. But in this case, it's not really the slope. It's a model coefficient for the input factor, which is x1, which is one of your test factors. And, you know, you can see that, well, here's your effect, and here's the slope. This is actually a difference between plus and minus. Okay. Now, two factors, two levels, you would look at this. Your equation would then go and look like this. And in the original case that we had, what we're looking at here is the yield is, remember, everything else was random error, so we can ignore it. We have x2 and well, x1, x2, x1 and x2. This would then become mixing time versus and power. The 66.5 was your average response that you calculated earlier in that table. This is the intercept for the equation. Minus beta 2, which is the coefficient for B, minus the coefficient for C times C, and then minus the coefficient for BC. And if you remember, we just gave you the equation on how to calculate these coefficients. Let me back up here. Okay, so you can see. Well, let me go back here further. Okay, it's this effect that you had. Okay, I think I may have missed that whole point. Anyway, this becomes your fitted model. And the thing is that you have to convert the levels of the actual input into coded levels, which are plus minus, and to make things a little more interesting. Okay, here's your thing. Your runs, B's and BC was a plus. You remember all of this. The predicted yield, the actual yield here is this. Now, if you take these numbers and you put them back into that equation, you can calculate your predicted yield. Your predicted yield, your predicted yield is this guy here, the y hat, for your various factors. And in this case, remember, we had a beta 2 x2 right here, and then the combination of the two. Here's your BC effect. Oops, what am I doing here? Okay, so anyway, this gives you your predicted yield, and then you calculate a thing called a residual. The residual is nothing more than the difference between the actual yield that you got for these experiments versus the residual, versus the predicted yield, which gives you the residual. And here we go. Down here, there's an example down here. So now we go into a normal probability plot. And in this case, you don't take your absolute values, you use your plus minuses. And now you've got 8 residuals that you've just calculated. And the midline, you use what is called normal probability paper. And again, I would say you need to have a software package for this. You can do it by hand again. The normal probability paper looks a little bit different, but you can do this and you can look to see if the residuals are normally distributed. And if they're not, then you're going to have significance. Notice this, in your normal probability paper, the lines get closer as you get closer to the center. Remember, you got a curve that comes up like this and then down and up. And so what you're looking at is it's spaced wider at the ends. And then in the middle, where you come to the peak of your bell-shaped curve, the lines get closer together. So you would plot it on this type of paper, and that should end the session here. I'm sorry I had the confusion about how to calculate the beta 1 values, and you can go back and look at the notes and see where we've done that calculation. I lost track of the slides there. But at this point, I think we'll get Johnson in and we can open it up to questions.
Thank you so much, Dr. Kumara, for the wonderful presentation, and also all our participants for cooperating with us. It's time now for the Q&A to begin, and we request all those who have questions to click on the raise hand option, which is a palm-like icon at the bottom of your participants panel, so that I can go ahead and unmute your lines and you can verbally ask the questions to our speaker. You can also go ahead and post your questions on the Q&A panel, and so that our presenter can read out loud and then answer. For any reason, if you're unable to ask your questions using either of these two means, please share it with me by chat, and I shall go ahead and pass it on to our presenter. Meanwhile, we sincerely request you to share your feedback. The feedback form will appear on your polling panel right now. It has about 8 multiple choice questions. It wouldn't take more than 2 minutes of your time to answer. The polling will remain open till the end of the session, and you can answer it even after the Q&A is over. Now that our Q&A session's open, in case any of you all do have any questions, please feel free to go ahead and click the raise hand option, and I can unmute your line so that you can ask your questions verbally, or you can also go ahead and use the chat box. Well, while we're waiting for, go ahead, Doctor.
One thing I wanted to say is that I've shown you a very simple basic design, which is convenient for teaching purposes. But some of you, of course, are running into more complex situations. I hope I've been able to show you how this study can be expanded by looking at more test results and calculating more effects. So hopefully, in your real life work, you'll be able to apply this basic design and go on to things like fractional factorials.
Thank you, Doctor. Just wanted to inform all our attendees that there is an upcoming webinars that is going to be presented by Dr. Kumara on the 11th of April. And also we do have a whole list of recorded webinars with us in our library. Please do visit our website, which is GlobalCompliancePanel.com. Now, in case any of your team members, colleagues, friends might benefit from this webinar, we are happy to inform you that it would be available in the recorded format, and you can purchase it from our website, or call us at 1-800-447-9407. Well,
also,
Doctor, I don't see any.
Yeah.
Yeah.
Well, let me point out one more thing, that, having completed this webinar, usually you don't have a question right now, but tomorrow you might think of something. In which case, please feel free to send your question in by email, and I will try to respond to it as soon as I can get to it.
Thank you so much, Doctor. To all our attendees, in case you do have any queries, questions that might arise after this webinar, please feel free to write to us, and we shall get that same answered by our presenter. Doctor, do you have any suggestions or parting words before we wrap up today's session? Because I don't see any questions coming up.
I think I've said all I needed to say, and we'll go on to other things in the future.
Thank you so much, Doctor. We are grateful to all of you for having taken part in today's webinar, and if you'd like to get in touch with us, you can send us an email to webinars@globalcompliancepanel.com. We welcome your suggestions and feedback or ideas on how we can improve our webinars. If you'd like to suggest a topic, either on-site or off-site, we will be more than happy to go ahead and assist you. We look forward to having you with us again sometime soon, and for your continued patronage on behalf of our presenter, Dr. Stephen Kuhara, and the Global Compliance Panel team, I would like to say thank you for participating in this webinar, and we wish you a pleasant day ahead. Thank you so much. Thank you, Dr.